All right, I want to start the next section about backscattered electrons with a question. And this, again, is in your quiz. So, how can we modify that Everhart Thornley or ET detector to detect only backscattered electrons? So see if you can think back to that diagram and what can we do to only detect backscattered electrons? Take a minute, think about that, write it on the quiz, and then come back and we will discuss. All right, so let's see how we can use that Everhart Thornley detector to detect backscatter electrons. And the real thing that we can do is, again, if you think back to that Faraday or collector cage, that was set to positive voltage to attract the relatively low energy secondary electrons, right? Well, if we actually reverse the bias of the collector cage, that will repel electrons in general. So that means that those low energy secondary electrons will not reach the detector, while the secondary electrons, while the backscatter electrons, those have really high energy. They approach what the incident beam is. And so those are obviously, they feel the sort of the negative bias of the collector cage, but they have high enough energies to overcome them. And so we can use it in this way. So basically, reverse the bias will repel all electrons, but lower energy electrons can't overcome that force, whereas the higher energy secondary backscatter electrons can, and they make it to the detector. So we can actually modify this ET detector to detect backscatter electrons. However, in real life, this is actually not done very often. So this is rarely used. But I just wanted you to realize that we could actually do it if we want. So the real way that we, or the most common way, I should say, that we detect backscatter electrons is to sort of to utilize the position. So we saw that the backscatter electrons are really kind of low angles compared to the incident beam. And so if we more or less put a kind of ring around the beam, so that basically at low angles relative to this beam, we can detect those electrons that are coming back up and getting backscattered. And so this is known as a Robinson, or there are some solid state silicon detectors that do this as well. And they're basically just below what we call the pole piece, which is the lowest part of the sort of lens assembly. And so this is put at very low angles so that those backscattered electrons are detected. Another thing about this Robinson detector is that you have to typically insert this into the position that it is. Otherwise, X-rays for EDS cannot be detected. So a lot of times when you use this type of detector, you'll actually have to remove and add it when you want to use it and when you don't want to use it. So that's the Robinson detector. Solid state silicon detectors are sometimes actually attached to the pole piece. And so that's a way of getting around that configuration. But basically, there's, the detector there detects electrons and transmits them and allows us to image with those backscattered electrons. All right, so just to kind of rehash what the backscattered electrons give to us. Again, I mentioned that they scale with atomic number. So we have two atoms here, titanium, silicon. Relatively speaking, titanium is more dense, has a higher atomic number than silicon. So there's more, basically there's more protons and neutrons to interact with. And so electrons will backscatter at a higher rate when the atomic number is higher. So we'll get more backscattered electron from titanium than we will from silicon. So if these two pieces of material are next to each other on a sample, we would see contrast from the detector, because the detector is going to get more from the titanium region than from the silicon region. And that's how we get contrast. And that's why we sometimes call that Z contrast or atomic number or phase contrast. All of those are kind of giving us the same idea. All right, so let's look at some images of the contrast that we see with backscatter. So this one's from your book. The quality's not great, but basically we have a secondary electron image and a backscatter electron image. So this one, you can still see kind of the topographical contrast that we get, and so you can still, nothing's unclear, right? You still see features in this, but hidden on that is that if you look on the backscatter electron image, this region right here, if you look at it closely, there's regions that are lighter and there's regions that are darker, right? So on that single piece, we actually have differences in contrast, and that's different phases that we see. And so that's the kind of the additional information that you get here that you don't get on the secondary electron image, because it's not giving you that difference from atomic number. All right, so let's look at another question on the quiz. So here's another backscatter electron image, and I want you to see what you can say about these different regions in the image based on what we've just talked about with backscatter electron images. So think about the different regions and what does that say relative to one another. Answer that question, come back, and we'll discuss this question. All right, so now that you've had a chance to look at this image and think about what this means, let's see what you've got. So again, from the backscatter, we know that it's dependent on the atomic number, and a higher number will give you more electrons because there's more backscatter. So those regions will appear lighter, right? More electrons means a higher atomic number, which means a lighter image, because that's our source, or a brighter image. That's our source of contrast. So what that tells us, is that these lighter regions here, the white regions, have a higher atomic number phase than this one, which has a higher atomic number than this, which has a higher atomic number than this, which again, you can go all the way to these darker regions, which have the lowest atomic number, because all those electrons are getting absorbed by the low atomic number material, right? So we can't say specifically what atomic number it is right off the bat, but we can say, relatively speaking, which has the lowest and highest atomic number phase. So that's useful information when we're looking at phases. All right, so let's look at a couple more. I've got a couple more images here on backscatter. So again, secondary versus backscatter. Here again, pretty nice image. You see a lot of changes from height in this image and grain boundaries. But over here, you'll notice this sort of triangular phase actually appears much darker than, along with this, than the rest of the region, indicating that that is probably a lower atomic number phase than the rest of these parts. So again, useful information to have. All right, so backscatter imaging we've seen. If we compare that to secondary, so we saw that region for secondary electrons, the escape depth was 5 to 50 nanometers. So they escape from a really surface sensitive area. Backscatter, however, because they are higher energy electrons, can escape from a much larger depth. And so we're in that case, we're talking 50 to 300 nanometers, right? So because of that, they escape from a larger depth. What that means is that they also have a lower resolution. And the reason I could say that is because if you if these electrons come from a larger depth, that also means that they come from a wider region of the material, right? So not just this narrow little region that the secondary electrons came from, it's this whole region. And so that presents problems and lowers the resolution because we're taking the electrons from a much wider area than we had with secondary. And so that's the spatial resolution that we talk about, and that's lower than secondary electrons. So there's an inherent difference between those two that we can't control for. All right, so there are things that we can do to kind of control the spatial resolution. So obviously, if we have control over the sample, if we have over here, if we have a higher atomic number, we backscatter more electrons, and it's from a shallower depth as opposed to the low atomic number. And so the resolution is going to be better because it's small. The depth is smaller for the high atomic number. So we don't usually have control over what our sample is, and so that's not a feasible way, but it is better resolution when the atomic number is high. The other more realistic way we can control spatial resolution is by adjusting the accelerating voltage. So going to a lower accelerating voltage limits the interaction volume and therefore increases the resolution because the depth is smaller. The depth and width is smaller here than with a larger accelerating voltage.